Well, thank you very much for having me, and I apologize that I cannot be here in person, unfortunately. I recently became a dad, and traveling for long distance is still a bit complicated, but I'm very happy that I can at least give a online talk about this very hot topic. I've already noticed, looking at the program of the workshop, that there was a lot of talks surrounding cosmic tensions and solutions. So maybe some of it will be a repetition, but sometimes repetitions are also good. So before talking about problems, let's talk about successes and remind that ΛCDM is an incredibly good cosmological model that relies on two principles, of course, general relativity and the cosmological principle of homogeneity and isotropy, and has essentially 6 parameters, 3 of which can be understood as describing the matter content, which sets the expansion rate. And that's how we know, of course, of dark matter and dark energy. 2 of which represent the primordial conditions, the primordial power spectrum and the physics of inflation. So this amplitude of the power spectrum, of the primordial power spectrum and the spectral tilt. And the last parameter is the one that is the less well measured. That's called the optical depth ionization, and that measures essentially the effect of star formation. And broadly speaking, the idea, it's a very good model to explain a whole variety of probes. And broadly speaking, the idea is to use information from early universe, in particular the cosmic microwave background and its beautiful 2-point correlation function in Fourier space here. The power spectrum has been measured by various experiments that are broad in broad agreement at 2 sigma. And we can calibrate this 6-parameter model and predict the behavior in the late universe. And this has worked very well for until, I would say, the past 5 years. But now that the cosmological model is under extreme scrutiny with higher accuracy measurements, we start seeing issues. Some that are more or less long-standing, such as, and I think we had a review about this during this workshop, the cosmic dipole anomaly and the question of whether the universe is isotropic. There are also questions about whether our universe is locally homogeneous, whether we live in a void. And there are a number of predictions that even if these 2 first problems were not a problem, if the universe was indeed isotropic and homogeneous, there are still a number of predictions that the ΛCDM model can make. In particular, I already mentioned the value of the Hubble parameter, the amplitude of fluctuation. We can test also for when realization happens, or we can test for the age of the universe. And as you know very well, as the precision of data has increased now, there is a number of tensions that have emerged. And so one might question, is this a sign of breakdown in the very fundamental aspects of the model, that is the cosmological principle or even general relativity? Or perhaps more modestly, and this is the approach that I'm going to follow here, but of course, the first approach is something that should be pursued, but I'm going to simply ask whether we are seeing the first signs of the true nature of dark matter and dark energy, which we should repeat in the standard cosmological model are purely parametric. And I'm going to focus on the Hubble tension today, the discrepancy in the Hubble parameter that is driven by the Schuss measurement. And this slide is already a bit outdated, but summarized essentially the procedure that the Schuss team has in order to measure the Hubble parameter. So the bottom line is really that they're trying to use the good old V, the velocity of the recessing velocity of object far from us is equal to the Hubble parameter times the distance, of course, modified because of peculiar velocities first, and also because of at high redshift, there may be additional term contributing to this just from cosmology. But in a sense, that's really the typical relation that they use. And when you write it in astronomy form, it takes this weirder shape, but this is really what we're talking about. If we know the redshift and we can measure it very good, all we need from spectroscopy, all we need is to know the distance to the object, and we can measure the Hubble parameter. Of course, the difficulty is that if you want to really get rid of peculiar velocities, you have to go very far away. So you have to use very bright objects, so supernovae, for instance. And you have to know the intrinsic luminosity of supernovae. So first, we know for a while now, and I'm not teaching you anything, that supernovae are type 1a supernovae are standardizable objects. The difficulty is knowing their intrinsic luminosity. And to know their intrinsic luminosity, it's a three-step process starting from the very local environment, in fact, even done inside of the Milky Way, but we have not observed directly supernovae exploding in the Milky Way, for which we have high accuracy distance measurement, in particular from the parallax. And so what is done is an intermediate step where they use Cepheids, but they have also alternative ways, or there are other groups using alternative ways. So what is done is to calibrate the period luminosity relation of Cepheids. So Cepheids are stars of variable luminosity that have a specific relation between the period of oscillation of their luminosity curve and the highest, the brightest they become during this in this period. And so this is called the period luminosity relation. And so if I know the distance to a Cepheid and I measure the period luminosity relation, I can calibrate that relation. Then I can find in much further galaxies, I can find galaxies that are host to both supernovae and Cepheids. And from my calibrated Cepheid diagram, I can calibrate the supernovae magnitude. And then I can go much further away in the Hubble flow. And from calibrated supernovae, measure the Hubble parameter. So this is really the 3 steps measurement. And this is just to show you that the current level of tension is at the level of 0.2 magnitude in terms of a mismatch. So you would need to find that we have underestimated the luminosity of supernovae by 0.2 magnitude. And even if it doesn't mean a lot to you, just keep in mind that it is about currently 5 times greater than the statistical uncertainty that they have on this sort of measurement. So what it means is that such a mismatch is very hard to have missed. So this is what it looks like when you look at the Hubble parameter. As I mentioned, it is, and you know, is higher by about 5 sigma, centered around 73 kilometers per second per megaparsec. So why our lambda CDM model predicts that is calibrated onto Planck data, predicts something around 67.5 plus or minus half a kilometer per second per megaparsec. So what are the sort of systematics that could be applied? I am certainly not an expert of this measurement, so I am not going to go into many details, but of course, this is a very important question that SHUS and other collaborations are taking very seriously. There could be issues in the Cepheid calibration. For instance, simply the period luminosity relations may not be the same for all the Cepheid, or there may be issues in how we have calibrated this. So we can try different ways of calibrating the supernovae. There may be dust issues. There may be crowding of Cepheids, so several Cepheid in the same image that bias the results. There may be issue in the peculiar velocity correction applied to the sample. There are metallicity correction applied to Cepheid. These may be correct or not. And of course, the geometric anchors, the ones that are really the first step of the ladder, may also be incorrect. For instance, it could be that the Gaia parallaxes are incorrect. So all of those are things that have been studied. And also, one could imagine something perhaps more drastic, that is that there are different populations of supernova. Maybe supernova are not exactly standard candle. Maybe there are several, the luminosity is different for different populations. And in particular, maybe the supernova that are found in galaxies that host also Cepheids, which are known to be galaxies with a lot of star formation, may be different from the supernova that you find in the Hubble flow at much larger redshift. So these are the typical questions that people have asked. And this is, if you wish, the one slide summary of this question according to the SHUS team. That is, regardless of about 70 changes that they did to the analysis to test and answer some of these issues, they can find no variation in the value of the Hubble constant by more than 1 sigma. So essentially, it's simple to say that currently, there are no known systematics that can fully explain away the discrepancy. Of course, more work is to be done still. But you can say, what if we look more generally beyond just supernova Cepheids? What is the status? Here is a summary plot of all the measurements that have been made. And what matters is to focus on, first, the indirect type of measurements. These are the ones that come from the early universe. Whether you use CMB data from Planck, CMB data, but other than Planck, or if you can even drop altogether CMB data and just use information from Big Bang nucleosynthesis. And the bottom line is that for those that are high accuracy, they all tend to give you numbers that are of order 67, while direct measurements in the local universe, whether using Cepheid calibrated supernovae or the tip of the red giant branch or other sort of ways to calibrate the supernovae or completely different ways of measuring the Hubble parameter, for instance, from strongly lensed quasar, typically give you large value of the Hubble parameter. This is a filtered way where I'm showing you the one that have uncertainties that are less than 3 kilometers per second per megaparsec. That's somewhat arbitrary, but this is just so that you can see the one that are really driving the tensions. And typically they are all much higher in the direct measurement than the predictions from the ΛCDM model. There is some debate between in the tip of the red giant branch that you may have followed, where the Schuss team and the CCHP team led by Wendy Friedman disagree essentially on some of the, I think in the analysis that has to do with things that are a bit beyond what I understand, but dust and so on and some measurements. So this is of course still debated, but you can see that there is a clear trend. Even if you ignore these things, there is a clear trend that the local measurements give you a higher value of H0 than the prediction of the ΛCDM model. So how can we change if we are being optimistic and assume that there is no systematic error? How can we change the prediction from the ΛCDM model? What sort of modification do we need to do? And for that, we should recall how the CMB data can measure H0. And it all boils down to measuring a standard scale called the sound horizon in the CMB. And what is truly measured by the CMB within CMB is the angular size of the sound horizon. The sound horizon, in case it's not clear for everybody, is the distance traveled by sound wave in the primordial plasma way before recombination, or until recombination, sorry, I should say. And so what is seen is the angle subtended by this typical scale, so the sound horizon divided by the angular diameter distance until recombination, until the last scattering surface. And the key observation to make here is really that H0, if you write things correctly, only appears in the angular diameter distance. This is the Hubble rate today. It's the expansion rate today. And it tells you how far from us the last scattering surface is. And also to remind you that H0 is nothing but the proportional to the total energy density today. The total energy density today is dominated by dark energy. And so you see that essentially what we're saying is if H0 is slightly higher, the total energy density in dark energy may be slightly higher, essentially. And if you were to adjust the value of H0, this is what would happen to the CMB peaks, because you're making this CMB last scattering surface closer or further away from us, depending on whether you increase or decrease it. You see that the CMB peaks would have mostly an horizontal shift. And then because of other characteristic scales that appear, in particular, something called silk damping, you can see also a little bit of an exponential tail that creates. But really, the dominant effect is a shift in the peaks. So how can we correct for that effect? Because of course, theta s, and I have not said it explicitly, I believe, but yes, it has been measured at very, very high precision. We know it extremely well. It's in fact the quantity that is the best measured in cosmological data nowadays. So how we certainly do not want to change the value of theta s. So how can we do that? Well, there's two ways that have been suggested. The first is to change the expansion history in the late universe, is to say, if H0 increase and can compensate that by changing the late universe expansion history such that the angular diameter distance to the last scattering surface does not change. So I want to compensate the higher H0 by changing the expansion history such that the angular diameter distance does not change. Alternatively, what you could say is I leave the late universe expansion rate unaffected, expansion history, sorry, unaffected, and I change the sound horizon intrinsic size, and I can compensate the fact that H0 is larger by decreasing the size of the sound horizon. So these are two, broadly speaking, categories of solution: late universe solution and early universe solutions. And I'm going to argue now that, unfortunately, the late universe solutions are disfavored by the data. So to be very clear again, the angular diameter distance can be explicitly written as an integral over the expansion history in the late universe. And you can see here the H0 parameter appearing. If I want to compensate for an increase in the Hubble parameter, I will have to decrease the fractional density of the various components. So I can either imagine a model where dark matter decays, for instance, such that there is less matter in the universe, or I can imagine a model where the dark energy density evolves with redshift. The simplest is to imagine that the equation of state is less than -1. So it's different from -1. And if we ask the data, in fact, so yes, of course, a lot of models that look at this sort of modifications. And if we ask the data just with the simple modification of the equation of state of dark energy, in fact, Planck data have very little constraining power. This is this gray constraint that I'm showing you here. Very little constraining power. And from the point of view of Planck and shoes, it's extremely simple to change, to resolve that tension. All you need to have is an equation of state that is less than -1. That might suggest some issues theoretically, but as far as the data are concerned, it is perfectly fine. However, we have a lot of intermediate redshift measurements of the expansion history. In particular, we have baryonic acoustic oscillations, and we have a whole suite of high redshift supernovae calibrated with shoes, for instance, but that are the Pantheon catalog of supernovae. And this is what forbids this sort of solution. And this is very generic, in fact. This applies to all sorts of modification that you can think of in the late universe. And the reason is really enrooted in the fact that in relativity, in general relativity, the angular diameter distance and the luminosity distance. So on the one side, the luminosity distance is what is measured by supernovae. On the left side, the angular diameter distance is what you measure when you measure the baryonic acoustic oscillation. Those are connected to each other by the distance duality relationship. So what happens is that when you use the BAO, you calibrate the BAO based on knowledge of the sound horizon from Planck that allows you to extract the angular diameter distance. At the same time, you can use the magnitude of supernovae calibrated thanks to shoes in order to know the luminosity distance to supernovae. And you see that you can play a game here where you can say, given that I know the sound horizon from Planck, I measure this from the BAO, I can extract dA. Then I can use the luminosity, I can use this relationship, and I can plug this back here to predict, for instance, the intrinsic magnitude. And this is really where things go wrong. If you do this, you find that the intrinsic magnitude is just wrong compared to what has been measured by Planck. And you see that regardless of whatever freedom you're going to give to the expansion history, nothing is going to change that fact. So if you just plot, what you can do is, given the sound horizon from Planck and the intrinsic magnitude from shoes, you can simply plot the luminosity distance measured by both BAO and supernovae. And you can see that they are in disagreement. The supernovae are here, the BAO are here. And these are curves that shows you essentially infinite freedom. These are really trying to adjust from the data, the expansion history. You can read the paper if you're curious how they do that. And the point is just that you would need some extremely weird oscillatory pattern that takes the Pantheon data at low redshift, then go back up to fit the BAO, then go back down to Pantheon, go back up. So of course, unless of a very, very weird oscillatory pattern, what you really need to do is to change the calibration. So in particular, you can either say that you don't believe in the shoes calibration, maybe you don't believe in the Hubble tension, and then there is no problem, or you need to change the sound horizon. And so this is the question: how can we change the sound horizon in order to make the inverse ladder calibration, which is using the BAO to predict the value of the magnitude, compatible with the measurement with shoes? So we need to reduce the sound horizon, and we can use the data to ask by how much we need to reduce the sound horizon. So essentially, choose data want the sound horizon of the BAO to be at around 137 megaparsec, while the standard lambda CDM model fit to Planck predicts something like 147 megaparsec. So you need to decrease it by about 10 megaparsec. But how can you do that? The sound horizon is simply the integral of the sound speed of this wave that propagated over time, which in redshift space is written like this. So you can say maybe the sound speed was different. Maybe the sound speed was a bit slower than what I predict. And this, you could imagine that it's related to some new properties of dark matter that is coupled with photon or with baryons. And I won't enter into the details of that. Essentially, it does not work because we have very high accuracy measurement of all the acoustic peaks that would that essentially forbid such a strong modification. The other possibility is that recombination happened at a slightly earlier time, that the redshift of recombination is a bit higher, such that the wave was frozen a bit earlier. So you can play with the physics of recombination to do that. And lastly, the possibility is that the expansion rate in the early universe was higher, the energy density was higher, or maybe gravity was a bit different, such as to increase the expansion rate. And these are categories of solution that invokes, for instance, new sterile neutrino-like species or early dark energy. And I'm going to now discuss this sort of solution. So the most naive thing that you can do is simply say that you have extra-relativistic degree of freedom, this an effective parameter that is usually parameterized at the background level by simply rescaling the number of neutrino-like species in the universe. So for the standard model, you would predict something close to 3. There is a very small deviation from 3 due to the fact that neutrinos have decoupled slightly after electrons and positrons and go out of the bath, but that's a small correction you can take into account. And standard neutrinos, since about a temperature of 1 MeV, behave as free streaming radiation. That means that they are not colliding at all. It's not a perfect fluid at all. It's just some free streaming radiation. And when we ask Planck about this possibility, looking first at temperature alone, we can, this is a plot that is a little bit outdated, but things have essentially not changed. Looking first at temperature alone, we see that there is indeed this degeneracy between the sound horizon and H0 as we increase the value of N effective. And in principle, with N effective that reaches something like 0.5 to 1, you could imagine resolving the tension. However, this is from temperature alone, and we have polarization measurements, and we also have baryonic acoustic oscillation measurement, as I have mentioned, that are two additional data sets that provide very strong constraints on an effective. And you see that as soon as you add this data, this possibility is really reduced. And in fact, even with newer data from Planck, and with even more complicated sort of modeling, maybe you have in mind that the neutrinos, your extra neutrinos are not free streaming. Maybe they are self-interacting, or maybe you have a mixing between a self-interacting contribution and a free streaming contribution, etc., etc. The bottom line is that this sort of solution, unfortunately, even if very appealing from first principle, are tightly constrained. Here, I should say that there are some subtleties, and if you're curious, I could discuss them in questions, but overall, the picture shows that this sort of models are disfavored by the data. So how can we do better than that? Let's go back to the drawing board and look at how the sound horizon evolved with redshift. And the first thing to notice is that the sound horizon evolves only very much towards late redshift. So it's very highly weighted towards a slower redshift. So what this means is that it in fact reaches the value of 10 megaparsec, and I recall that you need to decrease the sound horizon by 10 megaparsec only after a redshift of 25,000. What that means is that whatever you would do to the universe at redshifts that are larger than 25,000, You could even make this integral go to 0. You will not reduce the sound horizon enough. You really have to do it below 25,000. So essentially, what you want to do is find a mechanism that would insert, to say it crudely, new physics right in the redshift window between 1,000 and 20,000. And this is where the idea for something like early dark energy came about. So there are nowadays tons and tons of models invoking the presence of dark energy at early times that are this early dark energy. And if you're curious, we recently wrote a review, and also Mark Amukowski and Adam Ruiz wrote a review on the matter. And those two reviews, I believe, are very complementary. One gives more of insight on the Hubble tension itself. The other goes more into details of the model. So have a look. So what is early dark energy? The typical idea is really, is essentially what you do in physics when you have a problem. You put a scalar field, inflation, dark energy are the same ideas. You have a scalar field that is slowly rolling, that is frozen in its potential due to Hubble friction. And at some point, the potential term or the mass of the field is going to overcome the friction term, and the field is going to start to dilute. And one of the key things that you have to do, if you don't want to mess up the data, is have the field dilute faster than matter. So what you can do is modify slightly the action potential by putting a little, so this is an action potential that has a small exponent here. And this small exponent is not extremely well motivated from first principle. That's okay. What we're trying to do is simply have a handle on the rate of dilution of the field once it starts rolling down its potential in order to go faster than matter. But take this as a toy model. Of course, as I said, lots of people are trying to do better than this toy model with physical motivated model. But concretely, there are 4 free parameters in this model. There is, and talking here in terms of not of the model parameters, so in principle, you have the mass of the action, the decay constant of the action, you have the initial field value, and you have the potential, the exponent n. But you can translate all of that into things that the data care about. That is the total energy density, or the fractional energy density that is reached. And let me show you what it looks like. So the fractional energy density at some critical redshift. So it's the maximal energy density that is reached, after which the field is going to dilute. Then the critical redshift at which this maximum is reached, the equation of states, or this n parameter that tells you how fast or how slow the fluid is going to dilute. And the last parameter is the sound speed. And it's in fact tied to the initial field value once all of these 3 parameters are set. There are, as I said, more motivated model. If you're interested, you could imagine that a first order phase transition occurred, that you could change the potential, or you can even invoke some modified gravity that reproduce essentially a similar phenomenology. And when you ask the data how they like such a model, here I'm showing you the result of an analysis of Planck with Schu's data together. And they tell you that they would like to have about 11%, 10 to 11% of early dark energy at a critical redshift that is about 4,000. It's very close to matter radiation equality. And they are also able to really measure the initial field value. And I just said a second ago, that means they are really sensitive to the sound speeds, to the perturbation properties of that early dark energy. And in addition, compared to lambda CDM, there is a much higher spectral tilt, a higher cold dark matter density, and a higher value of that S8 parameter that I'm going to talk in a second about. And this provides a much better fit. The early dark energy model in this simple analysis would be detected and favored over lambda CDM at about 4 sigma. Of course, as you can see here, the S8 parameter has increased, and so one may wonder, and NS is much larger. So this has, of course, implication for inflation. And one may wonder whether this is in tension with galaxy clustering and weak lensing surveys. And I will talk about the S8 tension that I know you heard about. But first, let me briefly go and talk about the fact that you could use galaxy clustering measurements from BOSS to probe the model. in the linear matter power spectrum, the early dark energy model predicts about 5 to 10% increase in power at small scales. Here I'm showing you this 5 or 10% increase. Here you see the BAO features and the increase in power at small scales. And there has been a variety of analysis. The latest analysis we've done using an effective field theory approach to analyze both data. Essentially, currently, both data do not have enough constraining power due to the large uncertainties associated to nuisance parameter in the effective theory, or these counter terms, and the bias parameters. So have very little impact on the Hubble, on the ability of the model to explain the Hubble tension. But there are many challenges to early dark energy. So I've mentioned that the field, has to become dynamical, has to right around matter radiation equality. So this looks like a coincidence problem, a new sort of why then problem that resembles the why now problem as to why dark energy dominates about now. Well, we could ask, why did early dark energy start to be efficient about why then, you know? And this has triggered a lot of interesting model building in order to make this transition dynamical. The other possibility, the other problem, of course, is that the potential that we've used, and I have not said it explicitly, but the potential index that is favored is around 3. And that is, of course, not very well motivated, and it requires at face value some sort of fine-tuning of instantons if you were to take this potential coming from instanton expansion. But there is also a lot of interesting work in trying to understand whether these sort of models can be generated in string theory and progress being made. But of course, you could just look at different models altogether. Again, if we understand this, if we really take seriously the possibility of having some sort of axion-like particle in the universe, then it would mean that you have a decay constant for the axion that is about 0.1 of the Planck mass, and an initial field value that is about, that is very close, in fact, to the Planck mass as well. So it means you have some sort of fine-tuning of initial condition and near Planckian field excursion. And so people have invoked some constraints from the weak gravity conjecture potentially on this model. I think these are all very interesting constraints if this axion-like model is being taken seriously. But of course, again, this is something people are motivated at looking at different potential. And another of the problem that is a bit overlooked is a potential issue with the age of the universe, because in the early dark energy model, and in fact, it's very generic to many of the models that invoke new physics in the early universe, the age of the universe is going to change due to an anti-correlation with H0. Essentially, since we are not changing the matter density, but we are increasing the value of the Hubble parameter, the age of the universe is now lower. And this may come into problem with measurement of the age of the universe, for instance, from globular clusters. And there are interesting papers discussing this. Currently, uncertainty on the measurement of the age of the universe are too large to really constrain the model, but with advancement in this field, we may imagine that we are going to run into another problem with the age of the universe. So more generally now, looking beyond this simple axion model, as I said, there are many models that have been suggested, but they are all essentially giving you the same picture. I won't enter into the details, but the idea is they all isolate that something must have happened around matter radiation equality. They can, not all, but most of the model can bring the Hubble parameter up towards the Schultz value and reduce the tension to something between 1.5 and 2 sigma. They all seem to indicate a larger value of the primordial tilt and a larger value of the cold dark matter, which also means, similarly to what I showed before, a larger value of S8. And we will be able, with high accuracy, small scale CMB data, to disentangle between the model, between essentially the potential of early dark energy. And I should say, I'm not going to go into the detail, but you probably have heard that ACT data show preference for one of these models, this axion model that I presented. But this is a little complicated and would require more, a little bit of time. So I decided to skip it because there is some mild disagreement between ACT and Planck at higher temperature that gives a somewhat contrasted picture about this issue. But feel free to ask questions if you have, if you're curious. Let me, in the last few minutes, discuss more generally what other models have been suggested. And coming back to my simple distinction that I made earlier, there are late-universe models that change the expansion rate. I already mentioned that those were disfavored, but let me show you in practice again. And there are early universe models that can change the sound horizon. So I've briefly spoken about dark radiation models that change essentially an effective, and I've briefly spoke about early dark energy and its variation. But there are also models that play with recombination that are of interest. And in these papers, we've compared in a systematic manner about 17 different models that have been suggested in order. We compare them to the same data in order to really draw conclusions about what mechanisms are favored by the current data and what are the issues with all of this model. And just to be clear, we are differentiating two ways of interpreting what a good model is. One modest way is to say that the model gives a good fit to all the data, including shoes. This is what I introduced earlier for early dark energy. And of course, that the model is favored over lambda CDM by some measure of success. There is a more optimistic, perhaps more Bayesian inclined way, that is to say the model is favored over lambda CDM just from Planck data, essentially, and leads to a prediction of a high H0 without including the shoes parameter. So if you want, it's really sort of interpreting this as a bit simply. This is like saying I'm trying to get a good fit. This is the frequentist approach, while here I'm trying to be a Bayesian in a sense. And the results look like this. In green, you have the approach where we don't include any information about the Hubble parameter or the magnitude of supernovae at late time in the low redshift universe, sorry. Or in orange, we show you the results for all these models once we do include the intrinsic magnitude, the constraints from shoes. And what you can see, as I said, late universe model, none of the model can do much at all. When you look at the tension reduction, this column, all of the late universe model still lead to tension that are well above 3 sigma. Or if you look at preference, simple preference computation, they are all disfavored compared to lambda CDM. Moving on to this dark radiation model, again, this is what I suggested. It looks like it goes up, but when you compute tension, you still find above 3 sigma tension in most of the model, and they are only very weakly favored over lambda CDM. And the models that really do the best are this early universe model, but you can see that without any knowledge from shoes, these models are not particularly favored. And it is not necessarily a problem in the sense that Planck does not have to have enough accuracy to see this model. It's very interesting to note still that even with the shoes prior, the fit to Planck data is very good and the tension is very low, is much below 2 sigma in most of the models. Yeah? But it's certainly would be better that future, and I think is going to and will happen with future CMB data, that without even knowing anything about the intrinsic magnitude, these models will predict that it has to be in agreement with shoes. So this is really a bit of a summary picture of the situation currently. The best models are those that change recombination in the early universe, and in particular, the playing, and this is a bit arbitrary, but playing with the electron mass in this contest, and there are other, potentially there could be other ways. Essentially what you want to do is to change the recombination rate. You want to accelerate recombination, and one way of doing this is to play with the electron mass, or models that play with, as I said, early dark energy. However, there is another problem that I want to touch upon now that has to do with measuring the amplitude of fluctuation at small scales. This SA tension, and I know you've heard about it, so this is somewhat of a repetition. And this SA parameter is really a measurement made typically from weak lensing galaxy surveys that can be cross-correlated with galaxy clustering as well, and other probes. And typically it measures the amplitude in the gray band that I showed you. This is the sigma 8 parameter here, times omega m due to degeneracies that exist within the weak lensing measurements. And what it says And the left picture here is a little bit outdated because really what's happening now is that the latest measurements seem to tell you that the amplitude is slightly lower than the ΛCDM prediction. This is illustrated here on the left. The S8 parameter measured by this weak lensing and galaxy clustering measurement seems to indicate that it's slightly lower than what the ΛCDM prediction is. And that is a problem because all of the models that I've said so far are good at resolving the Hubble tension tend to go the other way. This is striking here for early dark energy-like models, but this also somewhat happens for this electron mass model or the models playing with recombination, which, if anything, barely do anything for S8. If they don't make it much worse, they don't really improve. So this means that if we understand, and if both tensions are not related to systematic, most likely it's going to require some additional dynamics than the simple model that I have suggested to you. And let's try to just understand what could be this additional dynamics. So I've mentioned already the S8 tension is really a sigma-8 tension. Even if for the reason that weak lensing is sensitive to S8, we talk about S8 tension, we have very good measurement of omega m. And the tension is really in the sigma-8 direction. Here, this is illustrated by comparing the Planck prediction for sigma-8 versus omega m to that of the kids surveys, and both cross-correlated, this red contour, where you can see that essentially the omega m direction is not in disagreement. It's really the sigma-8 direction that is in disagreement. And
Vivian,
yes?
Sorry, I mean, you have about 5 minutes to
Yes, this is my last slide. That's perfect. Essentially my last slide. So essentially what you can see is DES would like to be, or kids would like a suppression of power compared to ΛCDM in the sigma-8 scale range. And many models have been suggested to do that. And I'm not going to go into the details, but the bottom line is what it has been shown. And this is perhaps a little bit ad hoc and unsatisfactory, but that you could have a complicated dark sector where some early universe mechanism is responsible for solving H0, and some late universe mechanism is responsible for decreasing perturbation. On the left, I'm showing you the combination of a decaying dark matter model and early dark energy that could solve everything. And on the right, I'm showing you what could happen if you had ultralight axions as dark matter in the universe. So you have an ultralight axion that plays the role of dark energy and early dark energy, and another that plays the role of dark matter. And this could help in both directions, S8 and H0. The other possibility that is coming out right now, I think that people are really paying attention more and more, is that maybe sigma-8 tension is in fact due to the nightmare of astrophysicists and cosmologists, that is baryons, and that with an improved nonlinear and especially baryon feedback at small scales, the sigma-8 tension could be explained away. And this is a very recent paper that appeared, but there was some other discussion where by improving the modeling at small scale, by including more of small scales within DES, and by improving the modeling, they showed that baryons and improved modeling could reduce the tension to below 1 sigma. And this, of course, would have implications for whether these early universe models are in tension with this measurement that have yet to be investigated. So this is my conclusions. ΛCDM, as I said, explains very well a variety of measurements, but now with higher accuracy, we start seeing tensions. At the background level, it requires, to explain H0, you have to reduce the sound horizon at redshift around matter radiation equality. At the perturbation level, in order to explain sigma-8, you have to reduce power at scales of order 0.1 to 1 megaparsec. So H0 could indicate some new early universe properties. I mentioned early dark energy, maybe something to do with electron mass or changing the recombination physics. But typically, H0 solutions tend to make S8 worse. So you need some additional dynamics. And all of that could still be just that we don't really well understand baryons at small scales. In the future, we will have a lot, very high accuracy CMB data at small scales from the Simons Observatory, or even just from the next data release of ACT and SPT, that should be able to measure any deviation from standard ΛCDM at redshift of 3500. So we will have a definitive answer as to whether something happened at this redshift. And of course, we will also have better measurement of the sigma-8 tension, if you wish, with DESI, with Euclid, with the Vera Rubin Observatory. So everything should be settled really in the next few years. And even if the picture is a bit complicated so far, I should really remind you that ΛCDM so far is purely parametric. We only know CDM is a simple parameter, dark energy is a simple parameter of the model, and maybe these tensions are signs of a rich dark sector, and we should be happy. Thank you very much.
Thank you very much, Vivian. This was very, very interesting. Yeah. So we have time for a few questions. I hope that's fine with you, Vivian, right?
Oh, of course. Yeah, it's a pleasure.
Vivian, can you hear me?
Yes, I can hear you.
Okay, so first of all, nice talk. Thank you very much for that. For the nice talk. My question is, what if Hubble's constant is not exactly a constant? So what if the value of Hubble's constant itself is evolving over redshifts? So,
right. So I think what you're asking is, and I've seen these papers, yes. So what you're asking is whether probes at different redshifts, because I just want to say, of course, the Hubble parameter evolves with redshift is a fact, but what you're trying to say is H0 that is measured from probes of different redshifts when you extrapolate to 0 may be different. And yes, this is a very good diagnosis of some issue in the late universe. But I want to recall that, let's go back to my discussion here. Oops. I just want to recall that what you're saying is a byproduct of the fact that if you fit lambda CDM at a different redshift, and you ask what is the value of H0 from different probes, indeed, if you have the wrong evolution for omega m and if you just assume lambda CDM, but there is some additional dynamics at late times, then H0 may evolve with redshift because of the fact that you're compensating for the fact that you had the wrong model describing the expansion rate. That I just want to stress that people have investigated extremely large freedom. In fact, just asking all of the data at these various redshifts, whether you could find deviation that would explain away the tension. And the answer is, maybe there is some degree of variation between various redshift bins. That's not impossible, but certainly not enough to explain the Hubble parameter, to explain the Hubble tension. We know that the late universe expansion history is fairly well constrained. And this is true even if strongly lensed quasars tend to show a small variation in H0 and so on. We keep in mind that this analysis that let the expansion rate extremely free to vary should see a deviation if something was significant.
Okay.
And they don't.
Thank you.
You're welcome.
Yeah, sure.
Hi, Vivian. Great talk.
Hello. Thank you.
So I have a question regarding the plot by Adam and group on systematics from supernova.
Right.
Yeah, so do you know whether they have tried to see whether the population of supernovas which are particularly driving the measurement, like with less error bar, are those having significant any correlation with metallicity properties or the stellar properties of the host galaxies? Did they do any that kind of systematic checks?
Okay, so yeah, so the simple answer is they certainly do. So for the metallicity, I'm not sure. I know that they test for the metallicity of the Cepheids, and not only do they test, they include the fact that there is a dependence on the period luminosity relationship on the metallicity. For supernova, we should open the paper and look. I mean, this is very clearly explained. What I do know, and I can explain a bit more, is this, and what you're saying is indeed, and it has been put forward that they have, there seems to be some indication, and in fact, it is known that there is a correlation between the intrinsic magnitude of the supernovae and the mass of the host galaxy. There is what they call a mass step. And of course, this is extremely weird because in principle, the supernova itself has nothing, should not know about the mass of the host galaxy. So people are trying to understand what is the origin of that. And what has been put forward by notably Michael Rigaud, collaborators of the Supernovae Nearby Factory, is that there could be a correlation between the local properties of star formation, so the star formation locally of the around the supernova, and and the luminosity of the supernova. What they have in mind is that there are two populations of supernova, what they call prompt supernovae and delayed supernovae. The prompt supernovae would come from young stars, white dwarfs that just collide and produce supernovae, while the delayed supernovae is what we have in mind, is this red giant that feeds onto a white dwarf that explodes. And because the Cepheids is associated with an environment where there is a large star formation rates, they believe that indeed the Cepheids could be tied to measuring essentially the population of prompt supernovae, the intrinsic luminosity of prompt supernovae. However, when you go in the Hubble flow, then you have a mixture of both population, and so you may be mismatching, you may be using a wrong intrinsic luminosity. You're applying the intrinsic luminosity of a single population to the whole population. And the answer is that, yeah, I mean, of course, the truth people are taking this very seriously, and the simple answer is that they do not see such an effect. I don't know if I can isolate which one it is on this one. I think they look at, yeah, I'm not going to be able, I don't know which one it is, this point it is. But anyway, they look at they have a way, they claim that they have a way based on the shape of the galaxy, I believe, whether it's spiral or elliptical, that is another estimator of whether it's an old galaxy or not. This is well beyond what I really understand. But anyway, they have a claim. They claim that they can test for these effects and they don't see it. So that's the first answer. The second answer is also that even given how strong the magnitude break is, in fact, it would not fully explain away. If you take the latest shift that are suggested by the supernovae nearby factory, even if you were to apply this correction fully, and again, the supernova Schu's team tried to do this, it would not explain away fully the Hubble tension.
Okay, thanks. Because you're seeing your other plot, which was on MB infer from supernova and infer from inverse distance ladder.
Yeah,
That's
yeah.
an interesting result, right? Because you can see that the discrepancy in the value of MB is not huge. So
no, but this is the point. I mean, this is because they have a high precision measurement. It's really the key.
Yeah.
This is what I was saying. The discrepancy you're seeing is 0.2 magnitude, and
that's all.
You can see it here again, and it's not big, of course.
So because
it's like between but it's much larger than the statistical uncertainty that they claim. So the point is, could they have missed a 5-order 4 or 5 sigma? Maybe you don't need 4 or 5 sigma. Maybe you need 3 sigma, and then the rest is statistical fluctuation. But this is the key. I mean, it's true that a bias, if there is a bias, there is no tension. But the biases are much larger, has to be much larger than what they actually are sensitive to. So it's not easy. It's not simple, and it has, of course, implication for what they measure. I mean, so it's not that easy.
Yeah, I understand. Thank you. Good to see you.
Hi. Thank you.
Okay. Any other, maybe a quick question? Okay. I don't see any hands up. So maybe then we can thank Vivian again for this very engaging talk.
Thank you very much,
Vivian.
Thank you. Sorry for not being here, but have a nice workshop. Bye-bye.